reminder. What are we doing on Wednesday? Meeting in the library, not here. And we're going to talk about, well, a few things. Final project assignment, but also specifically the three different tech tools that you can use for it. And Andrew Taylor, who is the runs the Ed Tech Center, will kind of give you guys a brief demo of each of the three tools, and that maybe will help you decide which one that you want to use. Um, and if you, does anybody have like lots of experience doing video editing or audio stuff from, yeah, like what? Okay. So what software did you guys use? Premiere? Okay. Yeah, Premiere and After Effects. Okay. So the three tools are Audacity, which is an audio mixer, um, Premiere Rush, which is sort of a stripped down version of Adobe Premiere, but if you're familiar with big Adobe, then feel free to use that. And then Adobe Express Web Pages, I think is what it's called. But Andrew will give us a crash course in the three different options, and hopefully you guys can, you know, pick one. We'll also talk about where you can get royalty-free content for like B-roll on video or background music or things like that that isn't copyrighted, so it's okay to use it as part of your stuff. Okay, so anyway, so where we were last time was we discovered the secret sauce is that if we logically and a number against one followed by all zeros, then we get exactly two possible results, either literally all zeros or one followed by all zeros. Since that's a binary thing, we can use that as the basis for making a decision. Okay, and what's so special about one in the first bit position and zero in the others? Well, which bit position do I care about if I'm trying to tell whether or not a number is positive or negative? The first or the far left bit position is the most, or is what determines that. Okay, so yeah, so our program here is going to detect negatives, and let's just say it this will load numbers from FD and or sorry from FE, just a single number. Sorry. Um, so we'll write out a one in case the number is negative and a zero otherwise. Here I'm thinking of one as true, it is negative, zero is false, it isn't negative. There's nothing special per se about the numbers one and zero, but yeah, got to put something. Okay, so there is the details. Okay, so one thing I wanted to mention, because I had forgotten about this, is John and I met on Friday to John Barker, who is working on the automated program that will take code and spit out assembly, I mean, spit out machine code. Um, and I had forgotten about one thing that we had decided over the summer, okay, which is we changed the mnemonics for a couple of things so that every mnemonic corresponds exactly with one machine operation. And I had forgotten about that. So the difference we decided was that we would use load LDR for when it's coming out of memory, but move when you're putting a particular number in. And I think we used LDR before, so that's my bad that I forgot that we were going to change that. And then the other instruction that copies from one register to another, which previously we had called move, we just said that's silly. Let's just call it copy and be done with it. Okay, so changed a couple of the mnemonics. Now, what I did not change, of course, are the opcodes. That's all exactly the same, and it has to be for it to run correctly. So yeah, just minor screw up on my part. Okay, is that okay? Yeah, just a change in a label. Nothing horrible. Okay, so, huh? It is horrible. you guess you'll permit me to, my God, why is everybody all of a sudden booking with me? Like Joe. So all of a sudden my phone is buzzing. Yeah. Okay, so first thing we need to do is load in the number from memory, right? And so let's do that. And so what's the instruction? We need to load register 1 with the contents of FE. Okay. What else do we need to load in for the purposes of this program? What was that? I couldn't hear you. Yeah, 1 followed by 7 zeros, which what is that in hex? You all fail. Okay. You can see that today's class is going to be off to as good of a start as the football game on Saturday. Too soon? Yeah. Okay. Well, I didn't lose the bell. Just saying. Okay. All right. So need the number 80 because that's this number. 1 followed by all zeros in binary is 80 in hex. Okay, got that. And then we need to do the ANDing. So let's AND register 1 and register 2. And where are we going to put that answer? Let's put it in register 3. Okay. And now we need to make a decision. So I need to compare register 3 to register 0. And register 0, therefore, needs to have a pattern in it, either all zeros or 80. Doesn't matter which one we pick. Well, it does in the sense that, like, if we pick one, it'll change the way we write the program. Okay, so I'm going to choose somewhat arbitrarily to put 80 into register 0. Okay, and I'm going to do so. Well, do I have 80 in a register already? Yeah, I have it in register 2. So can I just copy it from register 2 to register 4? Or sorry, 0? Sure. Okay. So I could do this. I'm going to just do copy register 2 to register 4. Great. 0, yes. 5, no, 3, sir. Okay. All right. So then I need to do the following. Branch on equal. I'm comparing register 3 to register 0. And where am I going to go? Well, I don't know that yet, so I'm going to put in a placeholder for this. And register 3 equals register 0 would mean that register 3 has the value 80 in it, okay, which corresponds to the case of a negative. Yeah, so let me call this placeholder is negative. Okay, and then so I'm going to use these things. They're called labels, but think of them for right this instant as just being placeholders. Okay, and then I've got two cases, right? The case that it is negative and the case that it's not negative. So what do I want to do if the number is negative? What did we say we wanted to do? Yeah, put the number 1 in FF. Well, I need to put that number into a register and then store it out to FF. And then what can I do once I've done that? Halt. Okay. So if the number was negative, we decided, okay, I'll write a 1 out to this memory address and halt. Good. What about if the number's not negative? What do I do? We'll just put 0, 0 in that same memory address. Okay, good. All right, so we're not finished, obviously, but what will happen if the branch instruction BEQ does not branch? Then the program will just go on to the next line of code, which is line 18 on the screen here. And if the branch does take place, we'll skip all the way down to line 23. Okay, so does that make sense? Yeah, and you can put basically as many labels in here as you want. So a label here is a thing followed by a colon. It's not an instruction itself. And so if I'm going to jump to is negative, what I'm really doing is jumping to the first instruction right below is negative. Okay, so Gucci with this. So take a minute, stare at it, question preguntas fragen, and then we'll keep going. Yeah, Curtis. No. Yeah, so like here, no. You only need it when it's sort of a label on its own. And that's true in most languages, so, or most assembly languages, so I'm just kind of mimicking here the real ones. Yeah, because those of you who want a CS major, right, everybody got signed up for CS111 for next semester, subject to the whole waitlist thing, which I'll sort out later. Yeah, okay. And then in the fall, you could take CS241, where you'll do real assembly. It'll be fun. Yeah. Okay, good. Of course, that unfortunately would mean that you'd have me 3 semesters in a row for class, which I don't know. And that's partway to a minor in McKinney, right? All right, so this placeholder, though, needs to get fixed, okay? And the reason is, let's go back to our table. What does the branching instruction require? I can't give it a label, but what I can do is tell it the memory address where the instruction that I want to jump to lives. So I have to give it a memory address. So it will be, in our case, which register we were comparing, number 3. So I would have something of the form B3 question mark, question mark. Okay. The problem is I don't yet know the question mark. And so we'll have to kind of go through one pass of figuring things out and then go through and fill in the question marks. Okay. Is that all right? Yeah. Okay. So let's start translating all of this stuff into the machine code. All right. So what's LDR? All right. 11FE. 2280 8312 4002, no, 20. And then finally, B3 question mark, question mark. We'll go back and fill in the question marks in a minute. Okay. All right, if we continue, this would be what? 2400 34FF C000 2401 34FF C000. Okay. So good. All I did was translate each thing according to the table. Okay. Now, what I need to think about next is, where is this program going to go for it to be executed by the processor? Where does the program get stored? In memory. Okay. Starting at what memory address? 00, right? The very first memory address of our machine. So let's go back to that, right? How much memory do we have on this machine? 256 bytes, okay? Starting with address in the top left corner of 00 and ending in the far right-hand corner with address FF. Yeah? Okay, and on this particular architecture, the program code must start in address 00. Not true about all architectures, but it is for this one. Okay, so that means that this instruction, 11FE, what memory address does it live in? And 00 and 01. Okay, why is it both of them? Because how many bytes does each instruction take? 2, and each memory cell is only 1 byte, right? So hence every instruction in this architecture requires 2 memory addresses. Okay, and so what I'm going to do is list 00 here to indicate that that's where that instruction starts in memory. Is that okay? All right, where would the next one be? Yeah, it'd be in zero, starts in 02 and finishes in 03. And the next one, 04, 06. You guys notice in the pattern? Yeah, 08, followed by what's next? You fell for the trap. I should have held up my Admiral Akbar poster, right? It's a trap. It's not 10, it's 0A because we count in hexadecimal, gentlemen. Yes? Yes, good. Okay. Followed by 0C, and then 0E, and then finally we hit 10, okay, 12, and 14. Okay, so we're just counting up by twos. That's all, right? Because each instruction takes 2 bytes on this architecture. That ain't no big thing. Okay, so now we have everything in front of us we need to figure out what question mark is here. All right, so take a moment to yourself and figure out what your guess is for question mark, and then let's see if you all get it. And I need to get a soundboard and stuff so I could play the Jeopardy music when I ask you guys these sort of semi-rhetorical questions. All right, who should be our first victim? Mr. Dickey, what do you think question mark should be? You want to phone a friend? Okay, pick a friend to phone. What did you say? I can't hear you because of the AirPods. 38? No. Curtis? 04? Nope. Any other guesses? All right. 10. Why? Where is the first instruction of is negative? At memory address 10. So that's where I'm jumping to. Yeah? Yes? Okay. Well, second quarter's not looking so good either. Huh? Yeah, it kind of was a. I mean, I think probably the only reason we got to score at all was because they started putting in their second stringers towards the end. No. So, yeah. Apparently, Wabash does not, in fact, always fight, but all right. I should stop rubbing it in. Okay. Huh? Yeah. Yeah, I'm kind of savage, right? No, it wasn't the chicken tenders. It's that not a single one of you came to my birthday party on Friday. Invitation. Yeah, I know. I'm kidding. I'm kidding. Yeah. Okay. So why is it 10? What's the memory address that contains the first instruction of the is negative label? 10. Okay. Now, here's the annoying thing. We had to go through and finish writing the program before we could figure that out, right? Because if I add 5 instructions up to this top part, what's going to happen with all these memory addresses? They're all going to shift and change. Okay. So you can't figure out the question mark part until basically the last step or second to last step. Is that annoying? Yes, but them's the breaks. Okay. So now the last step is I need to just type out all the instructions. Okay, basically I just concatenated them all into a big long line, right? And then take this to put into our simulator. Okay, is that all right? All right, so let me do that. Hand on your head when you're ready for me to go to the website, because I know some of you guys are scribbling at the moment. I don't want to interrupt that. Question? Sure. Okay, so why did I not do what now? Ah, okay. I could have, right? So the question is, why did I put the is negative stuff right here? And the reason is because what number did I put in register 0? 80, right? So if the equality is true, I need to go to some piece of code. And if the equality is not true, I'm going to move on. So because I put 80 in register 0, I'm jumping past the not case to the is negative case. If I had put 00 in register 0, then these two things would have been inverted. And uh, yeah, okay. So it's all because of the logic that I chose, right? Now, is the other way wrong? No, it's just a different way of writing it, right? You got two ways. Um, okay. So, any other questions about this before we demonstrate that it works? No. Okay. So let's plug it into the simulator and see what happens. Hopefully, it works. Okay. So paste, enter, and then don't forget to hit refresh. All right. I need a number here in this memory cell for testing. So let's start with just say 5. Okay, so what ended up in memory cell FF when all was said and done? 0. Okay, does that make sense? Because the number that was input, in this case, 5, is a not negative number. Yes? Okay, so let's change this to a negative number and see what happens. How about FB, which just so happens to be negative 5? But whatever, it's just a negative number. All right, so let's do the same thing. And what should get output in this case? A 1. And sure enough, it does. Okay. Now, what I'd like you to do is I'm going to rerun this, but I'd like you to pay attention to the program counter. Okay, so pay real close attention to the program counter. 2, 4, 6, 8, A, 1, 0. So it skipped over a bunch, right? Whereas if I put the 5 back, 2, 4, 6, 8, A, doesn't jump, C, E, 1, 0, terminates. Okay. So you see basically how the branch works is by changing the program counter. Now, one of the other things that John and Owen are working on is a version of this, but where it will highlight, like in color, which memory address is currently the program counter is currently pointing towards. Still working on that, but still have it. Okay, so that worked. Yeah. Okay. Well, let's look back at the code for a moment. And where was the memory address that we jumped to here? 10, which just so happened to be further along in the code. Does it always have to be further along in the code? Of course not. Right? So if I can jump forward in code, can I jump backwards in code? Of course I can. Why not? I can't do that. It's annoying. Yeah, well, if you didn't want to have annoying stuff, you should have not taken the class. So, okay, so I can jump basically forward or backwards in memory and re-execute code that has already been executed. Now, why might that be a good idea to be able to do this? What might this enable us to do? Can do loops, right? And as we've seen before, loops are useful. Okay. All right. So let's do a, oops. Let's do some simple addition. Okay, if I want to add two numbers in this language, right, I can just do it. I have the addition opcode, right? What would be maybe a silly way to do addition without doing addition? This is kind of a silly question, but yeah. Well, okay, yeah, that's not quite what I meant. How did we do it in bare bones if we wanted to add two numbers? Yeah, we went through a loop, and what did we do each iteration of the loop? We incremented one variable and we decremented the other. Yes? Okay, so even though this is a really silly way to write addition, let's go ahead and do it because it illustrates a loop. Okay, so basically what we're going to do is translate the following bare bones code into assembly. So we'd have, say, init x equals 5. I'm just going to pick some numbers for sake of demonstration. Let's just do 5 and 3 because the sum of that is really obvious. Okay, and then I would do while y not 0 do increment x, decrement y, end, and that's it. Okay, so what's going to happen when this thing runs? Well, I have 5 and 3. Is 3 equal to 0? No. So I'm going to increment x. So now I've got 6 and 2, and then 7 and 1, and then 8 and 0. And now do I loop anymore? No, because now y is 0. Okay, and so the first number, x, is now 8, which is the sum of the two things. Okay, good. So that would be the bare bones version of it, and I think we've looked at that at some point. This version, it's certainly not the most efficient way of doing addition, but it'll work. Yes. Okay. So how am I going to translate this into the assembly? Well, the first thing I need to do is I need to get the number 5 and 3 from someplace. Why don't we go ahead and pull them out of memory, and that way I can change the numbers. So where should we put the numbers in memory? How about cells FD and FE? Right? Does that sound okay? All right, so let's we'll load register 1 with memory cell FD's contents. We'll load register 2 with memory cell FE's contents, and then we'll continue. What numbers do I need to have in registers in order to do this? Well, certainly I need the two numbers coming out of memory. So that'll be 5 and 3 when we run it, just for sake of example. Okay, got to have two numbers. But I also need a couple of extra numbers to work with, some auxiliaries. What are they? Couldn't hear you, sorry. 0? Okay. I need the number 0 as an auxiliary because I need to be able to check, hey, has Y hit 0 yet? Okay, so I need 0 as an auxiliary number. Good. What else? I need 1 and -1 as the auxiliary numbers to do the incrementing and the decrementing, right? And -1, okay, I can decrement by adding -1. All right, so 0 and 1, those numbers are obvious, but what's -1 in hex? Because remember, everything here is signed. FF, right? FF represents -1 as a signed integer, right? How do I know that? All right, what's the bit pattern for the number 1? All zeros and then a 1. Flip it, you get all ones and then a 0. Add 1, you get all ones. What is that in hex? FF. Okay, so let me load register 3 with the number 1. Oh, and that should be move. Let's put the number -1 in register 4. Okay, so that's the FF. And then let's go ahead and put 0 in register 0. Okay, so now we have the two numbers that we're trying to add, along with these 3 auxiliary numbers that are going to be part of the computation. Okay, so you guys buy that? Okay, good. So the very first thing that I need to do after I actually load in all these numbers is, well, I need to, if in bare bones I have while y not 0 do, I need to check, is y equal to 0 or not? Okay, so where is the number y? Where's my second number being stored? FE in memory, but which register? 2. So I need to compare register 2 to register 0, and if they are equal, that means that the second number has hit 0 and we're finished. Okay, so let me put a placeholder and call it finished. Okay, is that okay? So we would jump past a bunch of code if the second number has hit 0. It could have started at 0, or maybe we've decremented it until it's hit 0. Okay? All right. If that's not the case, what should we do to the two numbers? Increment 1 and decrement the other. Yeah? Okay, so which one do we need to increment? The one who's sitting in register 1, so I need to do add R1 destination, R1 input, R3 has the number 1 in it. Okay, so this will increment X. Then I also need to do a decrement of Y. So I'm adding 1 to one of the numbers and adding -1 to the other. Oui? No. Oui? Muy bien. Okay. Well, once I increment and decrement, what do I need to do? I need to go back up and check whether or not the second number has hit 0. So I need to jump back up to line 14. Okay, so I need to do something of this form. BEQ R something to the label loop. Okay, and then we're going to think about what the something ought to be. Okay, so when I hit the bottom of the loop, I want to go back up to the top to recheck whether the second number is 0. Right? Because after I decrement it, it maybe started as non-zero, but once you take 1 away from it, it could now be 0. So, but this BEQ, right, what does it do? It compares two registers. And if they're equal, it does jump. And if they're not equal, it doesn't jump. Do I always want to jump once I hit the bottom of the loop? Always, 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 always. Yes, I need to go back up to the top and then recheck. Okay. So this branch, the one on line 17, needs to always take place. How can I guarantee that can happen? It's where you have to think diabolically. Or just think. It's not so diabolical. Well, what does the branch instruction do? It compares registers something to registers 0. And if they're equal, it jumps. Otherwise, it doesn't. So how can I make sure that the contents of the register I'm comparing are always exactly the same as that of register 0? Compare register 0 to itself. Because no matter what's in it, it's equal to itself. Yes? Ah, okay. So we've just cracked how to do an unconditional branch. We'll compare register 0 to himself. Okay? Isn't that clever? No? Liam, you've got kind of a nasty case of RBF going on over there. Yeah. So, yeah. Okay, that'll take us back up. We'll recheck and then loop if we need to. All right, so what do we do when we're finished? Well, the second number is now 0, and we've got our answer. It's in the first number spot, so let's just store that out to memory. So let's store register 1 out to memory cell FF, and then we can halt. That's it. Okay, question, preguntas, fragen? No? This is fun. All right, so what's next? We got three things to finish. Keep going. Yeah, we've got one set of question mark to deal with, namely, where is finished? And for that matter, where is loop? Okay. We got to translate every instruction into its equivalent machine code, then make the long string and pop it into the the simulator and see if it all works. All right, so buckle your seatbelts. All right, so this will be 11FD, 12FE, 2301, 24FF, 2000, B2 something something. Let me put a space in here just to make it easier to read. 5113, 5224, B00 question mark 31FF C000, and then we can start putting the memory cells. So 00, 02, 04, 06, 08, 0A, 0C, 0E, 10, 12, and 14. Okay, so just counted basically through the memory. And all I did, right, was use the table, which is memorized in my case, but you guys will have the table. And now we can answer the question of what are each question marks. So, Mr. Dickey, for redemption points, what is this set of question marks going to be? 1, 2. Okay, the first instruction right after the finished label. Okay, and Safal, for redemption points, what's the second one going to be? Oh, say it again. A. Yes, good. Okay, so the first one jumps past the loop body. The second one takes us back up to the top of the loop. Okay, good. And then finally, what do we just need to do? Yep, just copy it all out. 12FE, 2301, 24FF, 2000, B212, 5113, 224, B00A, C31FF, C000. Done. Okay, so hand on your head when you're ready for me to move to the simulator. Or remind me next time and I'll pass out the cups again, the red, green, yellow cups. Yeah. Okay. Do we have hands on heads? Yeah, we good? Okay. So, you gonna live over there? All right. So let's put it all in. Hit refresh. Okay, and then we need two numbers. So let's put 05 here and 03 there. Okay, good. All right, so let's watch it, make sure it works. Okay, so it's loading in the auxiliary numbers and then checking the second number if it's 0, incrementing, decrementing, going back up to the top, checking, incrementing, decrementing, going back to the top, checking, incrementing, decrementing, going back to the top, checking. Oh, now we've hit 0, store, and halt. And sure enough, what do we get? 8. Well, that's cool. Surprise, addition works. Okay. Now, would you actually do addition this way? Of course not. You've got an operation to just add two numbers, right? But what this illustrates is what? How to do a loop. or a kind of thing where you might want to do a loop. Okay, there are plenty of things where you wouldn't want, or where you could do a loop, but you wouldn't. Well, okay, let me back up. What about if we wanted to do multiplication, for example? Right. Well, how did we do multiplication? I could add a number to itself that many times according to the other number, right? So this could be translated without too much trouble into a simple multiplication program. And I'd think of 5 times 3 as being 5 plus 5 plus 5, right? So two additions, that's one less than the other number. I think we even wrote a bare bones version of that. Okay. Yeah. Okay. So we could do this with multiplication. Now, is that the best way to do multiplication? For small numbers, it's okay, but it's not in general the best way to do it. Then you could ask, well, what about if I did it grade school style? Like, how did you do well, okay, maybe 5 times 3 is not the best example, but like, let's say, how would you have done 11 times 5 in grade school? You would have said, oh, well, I'll do 5 times 1 is 5, and then I'll shift over and I'll do the 5 times the other thing is 50, and then I'll add those two results together and I'll get 55. Yeah. So you could kind of think about multiplication that way. Has anybody ever heard of so-called Russian peasant multiplication or Egyptian multiplication? Okay, I'll show you guys that later. Um, there's lots of different multiplication algorithms, and um, if I may wax poetic for just a brief moment, so when I was in grad school, there was a course that secondary education teachers had to take, and it was mathematical methods for secondary ed teachers. So if you wanted to be an elementary school teacher and you were an ed major, you had to take this class, and it was taught by a guy who was sort of part time in the math department and his other part of the time in the education department. Okay, fine. And so, you know how we have the QSC and you guys can go and ask questions? Well, there's a similar thing where I went to grad school. And part of my duties as a graduate student was to work a few hours a week up in the math center. Okay, so students would come in from all kinds of classes to ask questions. And the student comes in with uh, stuff from this elementary ed class, and they were looking at Russian peasant multiplication. And I'm like, I've never heard of that. So I look at the book, I figure out what they're doing, I help the person through the problem, and then, but I'm thinking in the back of my mind, this is absolute moronic. Why would you ever do this? What's wrong with just the way that we learned when I was in school, damn it? Right? I had that moment, like, how many of you guys have seen the Incredibles, the second Incredibles movie, when um, Elastigirl is off doing something and Mr. Incredible is trying to help his son with his math homework, and they're like, "How could they change math?" Right? It was kind of that sort of moment. Um, and for years, I thought this was so stupid. And then I started teaching this stuff and figured out that in binary, actually, peasant multiplication is really slick and really efficient instead of the grade school method. It's like, now you're thinking with portals. Okay. Okay, anyway, so right, so we can do loops. Great. So basically, this machine and the instruction set we've got for it is enough to, well, it is Turing complete, right? We have everything that we have in bare bones. Bare bones is Turing complete. Therefore, this is too. Um, what we can't do with this machine, at least not yet, is recursion. Because it's missing a few things that would allow it to handle recursion. Uh, and guess what I've been working on for as a sort of research project is how to get recursion, how to do version 2 of this processor that would have the ability to do recursion. Okay, so let me quit the stream. I do have two quick pieces of business to discuss, and then you guys can go get food.